Hello, everyone, and welcome, and thanks for joining us to our webinar, Industrial Ceramics, today and tomorrow. I just wanted to let you know before we start that we're recording this session. When reliability, safety, and performance are critical, the materials behind the scenes matter more than ever, and that's where this webinar comes in, making ceramic selection more practical and less mysterious. In the webinar, we'll talk about how decisions are made, some of the common pitfalls to avoid, and what's coming next in technical and ceramic technologies. But before we start, let me introduce the panel speaking today. Myself is Ralph. I'm the CEO of RR Marketing and will be moderating this event. But I'm joined today by two Andaman experts, Gary Haitley, Director of the UK the divisions, and Julian Soom, Sales Director for France, who both work closely with customers on real-world ceramic applications across industries. We'll try and keep this practical and down to earth, and we'll leave time for questions at the end. So please do add them in the Q&A box, or keep a note of any that go through, and we'll get to them at the end. So before we start, can I just ask my two panelists to give a quick 30-second introduction to the audience?
Yeah, good afternoon, everybody. I'm Gary Haitley, as Ralph alluded to. I'm the Commercial Director for the UK and the US business, and my reach of responsibility extends globally outside of the EU. I've been with the company circa 15 years, and through that period have experienced a lot and gained a lot of knowledge from learned topics over the number of years that I've been with the business.
Hello, everybody. My name is Julien Soom. I am from France. I am 42 years old. I live in Paris, and I'm working for Andaman since 2017. And I am the sales director for Europe since 2021. And I'm working on the ceramic and the refractory sector since about 20 years.
Okay, hey, thank you very much and welcome to you both. So let's jump straight into the first question. So Gary, let's start with you. The first area that comes to mind is when a customer is looking to select a ceramics for extreme environments, what are the factors that really matter most?
Well, when selecting ceramics for any environment or application, and not just extreme ones, performance depends far more on application-specific failure modes than on simple strength numbers. So the most important factors shift depending on whether the environment is high temperature or corrosive, high wear, high pressure, or some combination of all of the above. We consider a number of critical factors that truly matter the most. First is probably the maximum operating temperature of the application. So establishing melting point alone just isn't enough. So it's far more important to understand things like creep resistance, phase stability, and strength retention at temperature. Example materials being, alumina being good up to around 1600 degrees C, silicon carbide, excellent high temp strength and oxidization resistance, and zirconia, strong, but phase stability must be controlled. The second being understanding the thermal shock resistance is critical in rapid heat and cooling environments. So examples of these could be things like turbines or engines or furnaces, and suitable material selection is generally dependent on four elements being thermal conductivity, coefficient of thermal expansion, fracture toughness, and elastic modulus. So an example being silicon carbide performs better in thermal shock than alumina due to high thermal conductivity. Point three is the mechanical reliability, and that goes beyond just mechanical strength. It's common knowledge that ceramic fail in quite a brittle manner and often without warning. So key properties for consideration being things like fracture toughness, which is resistance to crack growth, Weibull modulus, which provides a reading on reliability consistency, and fatigue resistance, especially important in cyclic loads and scenarios. Point four, chemical and oxidization resistance in corrosive or reactive environments such as molten salts, acids, combustion gases. Chemical stability dominates material selection, and factors to consider: oxidization resistance at temperature, resistance to molten metals or slags, resistance to hydrothermal attack, and compatibility with surrounding materials. Point 5, wear and erosion resistance for abrasive or particle-laden flow. This is where material hardness matters and grain structure and bonding matters more. So, for example, alumina and silicon carbides being commonly used in slurry pumps and nozzles due to their nature of being extremely hard. Point 6, which we alluded to previously, is the creep resistance, which is the material's ability to resist slow, permanent deformation, which is subject to a constant load over a long period of time, especially at high temperature. And under sustained load at high temperatures, ground boundaries sliding becomes critical, as does fine grade and coarse grain microstructures matters. Point 7, thermal conductivity needs to be here, and two extremes really matter. In very high thermal conductivity application, heat is generally dissipated, which improves thermal shock resistance, and widely chosen materials for such applications would be things like a silicon carbide. And in low thermal conductivity, such as thermal barrier application, we would lean towards a stabling zirconia. Think along the lines of a ceramic coating. And lastly, is the processing and microstructure control, which is often overlooked but critical. And we consider things like porosity levels, grain sizes, secondary phases, residual stresses, and sintering methods, such as whether the production method is to be hot press or isostatically pressed. And in extreme environments, microstructure design can matter far more than base chemistry.
And Julian, from your experience, do customers sometimes focus on one factor, like temperature, and overlook the others?
Yes, it happens, because we could say that most of the customers focused on max temperature and they forgot all the factors that Gary said before. I just want to give you the example of dense alumina. Most of the customers maybe have a process around 1,600 degrees. Then they said, oh, dense alumina, we could use it. But you have to take in account of, as Gary said, thermal shocks. We have to take into account mechanical shocks, pollution, etc. So it's why you need to have the advice from a ceramic expert before to choose the material, because it could work, but sometimes it doesn't work. So you have to take into account about that.
Yeah, thank you. And you've mentioned, Gary and Julian, a lot of different types of ceramics. So Julian, how do all these different ceramics actually differ in the real world applications?
Yes, so you have many different ceramics material like alumina, zirconia, silicon carbide, boron nitride, etc. These are all different, and we are using that for different application. Also, you have to be careful. For example, for alumina, you have dense and porous, so they perform very differently together. So it's why also I just want to recommend you to ask an expert to define with you the convenient material for your application.
And Gary, do you sometimes find that clients ask a specific material before they've even defined what they actually need it for?
Yeah, it happens quite often. Customers, especially in areas such as aerospace or energy, semicon, and industrial equipment sectors, sometimes specify a ceramic material before the application is fully defined. Usually, this occurs because maybe historically they've used the material successfully in the past, a competitor perhaps has used it, or the material itself has a strong brand recognition, and it appears to meet perhaps a single headline property, such as highest temperature capability. But the problem is ceramics fail based on interactions, not datasheet strengths. So I can provide two historic scenarios where this has happened, including some notable failures. The first one being a customer demand, we want zirconia because it's the toughest ceramic. Well, zirconia is often requested because it has unusually high fracture toughness, well, considering for a ceramic. What goes wrong is, in the example of a partially stabilized zirconia, it can undergo phase transformation, low temperature degradation and volume expansion and micro cracking. A real world example of this is in the early 2000s for medical implants. It was experienced unexpected degradation, which was exposed to body fluids over time. The most well-known case involved hip implants, which saw premature failures due to phase transformations in zirconia heads. The root cause of the failure is that the material selected for toughness before long-term environmental stability was fully characterized. The second example is, let's use alumina. It's cheap and it handles high temperature. Alumina, as we all know, is widely available and is generally considered a cost-effective and a chemical stable material. But alumina has moderate fracture toughness and relatively low thermal shock resistance. We have experience of industrial furnace components and mechanical seals cracking prematurely because designers underestimated thermal gradients during startup and shutdown cycles. In early iterations of ceramic turbochargers, we're talking 1970s to 1980s, alumina-based ceramics were evaluated long before the application, loading, and thermal gradients were fully understood. So thermal shock and reliability issues contributed to an abandonment of some designs. The reason for the failure in this example being temperature rating was considered, but unfortunately thermal gradients and flow sensitivity were not.
And Gary, what would you actually say are the most common failures you see day to day now? You've shown some really good examples of what's historically has happened, some of the high profile ones, but what would you say as the more day to day ones that you see?
Ceramics don't usually yield or bend like metals, so they fall and they fail in predictability, but in unforgiving ways. So in real world engineering application, a small number of failure modes account for the most ceramic component failings. The most common ones being, as I think I mentioned in one of my previous answers, that ceramic is a brittle fracture, or otherwise seen as a catastrophic fast crack growth. So the most common overall mode being that ceramic contains microscopic flaws, pores, inclusions, surface scratches, etc. And when tensile stress reaches a critical level, a crack propagates suddenly, which is triggered by tensile strength or surface damage and stress concentrations, as well as improper mounting. And why this is dangerous is there's normally no warning, and in most cases creates an instant failure. Slow crack growth is very common for ceramic in application. It's quite often misunderstood. So cracks grow slowly over time under sustained stress, potential environmental moisture, and elevated temperature, and eventually the crack reaches critical size, with the net result being sudden fracture. And this is common in aluminas in humid environments and zirconias that are exposed to water vapor. Water-assisted crack growth is a major life-limiting mechanism. We've talked about thermal shock and the effect that has on cracking. So that occurs when temperature gradients create internal tensile stresses. So cold fluid hits hot ceramic, rapid furnace ramp up and cool down, or emergency shutdown and cool down. So materials with low thermal conductivity and high expansions are especially vulnerable. For instance, silicon carbides handles thermal shock well. Alumina is slightly more sensitive, and thermal shock failures often show radial or surface origin cracks. There's a few of them. We talk about creep ruptures, and I could probably talk about this topic all day, so I think I'll pass it back over to Julian.
Yeah, I just want to say that most of the cracks we could see, it's thermal shocks, but also it could be design and bad specification. So yes, you have to take in account, as Gary said, that you have to choose the right material.
Yeah. Okay. And Julian, how does the manufacturing method actually influence performance and reliability of ceramics?
In fact, you have different manufacturing methods for ceramics. You have slip casting, you have pressing. It could be for pressing dry, wet, or isostatic pressing. You have extrusion, you have injection, 3D printing, and also full machining. This is the most common shaping manufacturing method. It could influence many things. the mechanical strengths. It could influence the thermal shock resistance, the resistance to cracking, and therefore also at the end, the performance and the reliability of the materials. Also, you could have a combination of several manufacturing methods like pressing, pre-firing machining, and post-firing machining. So it could help you to improve the final accuracy of the part. So you have also a last thing you have. Don't forget that manufacturing method could also impact the tooling price. It depends. It could be a huge or small one, a small price. The unit price of the part. It depends which one you are going to choose, and also the lead time. Machining is really shorter than pressing and casting, extrusion, etc. So you need to be careful about that. It depends what you want, the lead time or the prices. So
and then that's a very good point, actually, Julian. So how do customers balance the performance needs with cost and lead times? Because obviously, first things to probably think about cost and speed, but how do you help them sort of manage that sort of process?
We can say, Gary, sorry.
Oh, thank you, Julian. Customers balance ceramic performance, cost, and lead time by defining minimal viable performance rather than chasing, the highest spec material. And that's where Andaman's come in and help lead those types of conversations. And we've worked with our clients in applications where historically, let's take an example of a silicon carbide material that would have been used for a temperature capability and move them to an alumina body due to thermal loading perhaps, or being moderately more cost sensitive than the previous requirement. So when working with clients during the early stage of an inquiry, we really put a lot of effort and emphasis into evaluating life cycle costs, considering things like maintenance and downtime risk against just upfront material price and tooling expense. Standard grades with establishing manufacturing processes really reduce lead times compared to things like custom formulation, where R&D perhaps might be involved, which carries obviously an additional costings. So early client collaboration, clear operating parameters, and realistic reliability targets help prevent over-engineering while avoiding premature failures.
Thank you very much. So looking ahead, what new applications or processes do you see shaping the future of ceramics? Gary, maybe you've got some answers to that.
Yeah, for sure. I think the future is very exciting for the world of ceramics. And one thing's for sure, the boundaries are going to only ever be pushed further forward to the expectation of what ceramics can withhold. So several processes are poised to reshape high-performance ceramics over the next decade, certainly as we foresee it, and our market research to date suggests, especially in things like energy, aerospace, electronics, and very, very harsh and extreme environments. We see the demands of ceramic to withstand ultra-high temperature ceramics, and there's a lot of literature around zirconium diboride and hafnium carbide. These survive, or supposedly survive, temperatures above between 2000 and 3000 C, and are critical for things like hypersonic vehicles or atmosphere re-entry systems and advanced propulsion. And the future impact being better oxidization resistant coating and fiber reinforcement will make the ceramic less brittle and more flight ready. We're seeing ceramic matrix composites such as silicon carbide fiber reinforced already being used in things like jet engines, and these are critical because they have a higher damage tolerance far behind monolithic ceramics. They're lower in weight than superalloy, and they have higher temperature capability. And the future trend being the need for ceramic to have improved interfaces and oxidization resistant matrices for long service life. Another area is additive manufacturing of ceramics, such as 3D printing methods now allowing far more complex, intricate internal cooling channels, lattice style structures, and rapid prototyping, with the impact being increased design freedom, reduced tooling costs, and faster iteration cycles. And now the challenge, however, remains shrinkage control and defect reduction during sintering. And I think lastly, from my side, high entropy ceramics, which is inside by high entropy alloys. These mix multiple principal elements in near equal ratios. Examples would be multi-cation carbides and borides, with advantages being an enhanced thermal stability, slower diffusion, resulting in improved creep resistance, and tunable properties. And this is very much the material for the future, and is still largely in research stage, but should be considered promising for extreme heat and radiation environments. So the big picture trend is the future isn't just stronger ceramics. It's far more damage tolerant, more oxidization resistant, more complex in geometry, and more integrated with ceramic design.
Excellent. And Julian, have you got anything you'd like to add to that?
No, I just wanted to say that 3D printing is really the future for ceramics. Today, for some difficult parts, yes, as Gary said, the tooling cost is most of the time could be a problem. And also today, for 3D printing, it's impossible to make big production, but maybe in 2, 3, 5 years, we are going to remake a webinar, and my reply is going to be totally different. So I think, yes, 3D printing is one of the future for ceramic.
Excellent. So Gary, where do you see the strongest demand or growth for ceramics?
Semiconductor manufacturing, we foresee very strong growth, which is going to be driven mainly by AI chips and advanced nodes. Key uses being for things like wafer handling components, plasma facing parts, electrostatic chucks, and insulators in etching and deposition tooling. The materials along the lines of aluminas, again, silicon carbides, alumina nitrides, those kind of bodies of material. And the growth driver here is pretty clear, and the expansion is due to the significant investment in manufacturing, the likes of the United States, in Taiwan, in Korea, and in Europe. Further beyond that, the aerospace and jet engine as high value growth. The shift is moving towards lighter, hotter running engine, which is accelerating the adoption of ceramic matrix components, or otherwise known as CMCs. Examples being silicon carbide-based CMCs that are already being used within turbine components, something I've touched on in one of my previous answers. And the growth is so strong as a result of higher fuel efficiency targets, emissions, global emissions pressures, and the military's hypersonics programs globally. And we're already seeing as well an expected growth trend to continue in the global electronification and power electronics. Electric vehicles and grid electrification need substrates, they need power module insulation, they need thermal management components, again, material specialists, things like aluminum nitrides and silicon nitrides. We certainly see a big growth going forwards, and obviously battery storage as well.
Excellent. And Julian, do you see the same trends with your customers?
Yes, of course, we could see the same trends, semicon, aero. I just could add 2 other markets. One is defense. Unfortunately, I could say, because it's because there are war everywhere. But yes, on defense, we could deliver alumina parts, Segers, etc. And unfortunately, there is a big development on this side. And also luxury for us in Europe, where we could use more and more alumina parts, silicon carbide parts for firing support. There are big development on this kind of sectors, yes.
Excellent. And Julian, I think you alluded to it earlier, but when should a client start thinking ceramics might be the right option?
Yeah, of course, I think you have to think about ceramics when you meet difficulties in application where you are using plastic or metal parts. So we could say at this moment, maybe the ceramic option could be evaluated. We could say that ceramic is really more expensive than plastic or metal, but if you have a problem, if you want a bigger lifetime, maybe you have to use ceramics.
And Gary, do you see this often as a performance upgrade rather than just a first choice?
Yeah, sure, most certainly. It's normally through default rather than design. And as our clients are attempting to push the parameters of their process, we will be engaged to support them in doing so, utilizing our expertise in ceramic materials, combined with our learned knowledge and experiences. You know, Andaman's have been trading 75 plus years, and there's a wealth of knowledge within the organization that we draw upon.
Excellent. And finally, just a quick final advice from each of you. Julian, what's one lesson our audience should remember?
Oh, I said before, do not select the material with the highest maximum operating temperature or highest purity, thinking that it's necessarily the best one for your application. Please ask a recommendation from a ceramic expert.
And Gary, one practical takeaway from your side?
Yeah, along the same kind of lines, Ralph. One practical takeaway would be to involve Andamans early to avoid costly misspecification. In advanced ceramics, failures stem from choosing a bad material. They normally result from a mismatch between the microstructure or the environment, the stress state, and the manufacturing constraints. So Andaman's value really lies in the translated application conditions, thermal gradients and chemical exposure, load cycles, lifetime targets, all of those encompassing into the right material grade and processing route. That reduces over-engineering, shortens development cycles, and improves supply reliability. So instead of selling a catalog item, expect guidance. Expert guidance will help you select a ceramic that meets performance needs while controlling costs, risks, and lead times.
Excellent. Thanks to Gary and Julian for sharing all their insights. If anyone does want to ask any specific questions afterwards, you can feel free to email through to us. Or if there's any application you want to just talk to the Andaman team, please get in touch. If there are any topics you'd like us to cover in future webinars, let us know as well, because we are going to be doing more of these to try to share sort of knowledge and expertise. So please do let us know. So just to say, finally, thank you very much, Gary and Julian, and thank you very much, everyone, for joining us.
Thank you, everybody. Take care. Bye-bye.
Thank you.